Can anyone tell me what a mole is?
Quantity of atoms.
Okay, yeah, it's a quantity of atoms. It's how we quantify either atoms or molecules. And it's on the same premise of like a dozen. So if I say I have a dozen of eggs, how many eggs do I have?
12.
12. Okay. So mole is the same concept, but we're using it for chemistry. So if I say, let's say, if I said I have 1 mole of, let's say, carbon, does anyone know how many molecules or atoms that would equate to?
12.
So 12 equals a dozen, right? So a mole is a different number, but it's on the same premise that a mole represents a set quantity. So I'm going to tell you what a mole equals. So a mole equals 6.022 times 10 to the 23rd. Molecules or atoms. So if you say you have a mole of anything, 1 mole of carbon, 1 mole of gold, 1 mole of ice, 1 mole of lamps, it's always going to end up being that you have 6.022 times 10 to the 23rd of that item. Just like if you say you have a dozen of anything, it means you always have 12 of that item. And how we get this number is that carbon, which is the focus of a lot of things on Earth, 12 grams of carbon, 12 grams of carbon 12 to be exact, 12 is equal to the same thing, is equal to 6.022 times 10 to the 23rd molecules of carbon 12. And what this is called Avogadro's number. So this 6.022 times 10 to the 23rd is Avogadro's number. So Avogadro's number or Avogadro's constant. And you'll see it represented by N subscript A. And we use this to help quantify how much of an item there is. Because density plays into things, because you can say, oh, give me 5 grams of iron and 5 grams of gold. And those are going to be, those two objects are going to take up a different amount of volume. So if we want a specific volume for something, we could ask for moles, and that's going to give us a very specific amount of molecules to work with, which we need to have for experiments. So just make sure. So if I asked you guys to tell me how many molecules are in 0.25 moles of ammonia. Moles of ammonia. How would I convert this into molecules?
Would you have it divide by 6.022 times 10 to the 23rd?
Yeah. So we can start off with 0.25 moles of ammonia. then we can divide it or put it on the bottom. So 6.022 times 10 to the 23rd molecules. And 1 mole on top. Or, oops, my bad. Mix that up. Been a while since I've taught. So if we want to transfer it or convert it into molecules, we want molecules on top. Molecules and moles on the bottom, so that moles cancels out, right? For every 1 mole, there are, like you said, 6.022 times 10 to the 23rd molecules. That's going to get us a very big number, right? So how many molecules do I have in this 0.25 moles of ammonia?
You have 1.5 times 10 to the 23rd power.
Okay, yeah. So I have 1.5 times 10 to the 23rd molecules of ammonia. So if you notice, new concept, we're working with Avogadro's number of molecules, but it's set on the same stuff that we were learning earlier in the semester. So it's still dimensional analysis. Okay. So this is how I view it. This is one side of a triangle that we look at. So moles is going to be the peak. Dr. Henry, do you mind muting yourself?
Oh, sorry.
Thank you. Okay. So moles is a peak of this triangle. And on one side, we got molecules / atoms. But on the other side, we have grams. So if I have moles, does anyone know how I can get from moles to grams?
Could it be by using dimensional analysis?
Yeah, we can use dimensional analysis, but there's a specific name to the conversion that we do to achieve this. Anyone have idea?
By the molar mass.
Yeah, we want to use molar mass. Molar mass. And what is molar mass represented by? What units?
MU.
Okay, we have AMU, which is atomic mass unit. Anything else?
Oh, that would be grams per mole.
Yeah, in grams per mole. So grams per mole.
So it is molar mass AMU?
Yes. No, it's not.
So isn't AMU formula mass?
Atomic mass / formula mass. So we can use AMU when we don't necessarily know the quantities that we're dealing with, if I remember right. Like if we don't know if we're using grams, milligrams, stuff like that, if we're doing it purely theoretical, we can we'd be using AMU.
And more importantly, you're using it when you're talking about like the molecule itself, a single molecule or a couple of molecules. You're not looking at it when you're talking about more than that. You're probably going to be using like so one is a micro scale and one is a macro scale. Grams per mole is when we're talking about a macro scale, large amounts, something that we need to work with our hands.
And this is why he gets paid to be a professor and I get paid to be a TA. So yeah, so when we're talking specifically about molar mass, we're going to be leaning towards this grams per mole. So
And
we
if you
can
look at the name, sorry to interrupt
ahead.
again, but if you look at the name molar, moles, right? Mass, we use grams for mass, molar mass. So that should kind of help you remember mole, grams per mole.
So if we look back at the carbon 12 that I mentioned earlier for Avogadro's number, if we look on the periodic table, what does it tell us? What numbers are there to give us a hint?
What was that again?
So if we look at carbon 12, what is the mass of carbon 12?
Oh, would it be 12?
Yeah, it's 12. But if we're looking on like the macro scale, like Dr. Annie told us, if we want 1 mole of carbon, we are going to need 12 grams of it.
Over mole?
So the molar mass of carbon 12 is 12 grams per mole. And we can apply this to bigger compounds as well. It doesn't just have to be single elements like this. We can also find the molar mass of things like calcium fluoride. And how we do this is we want to know how many of each element are in this compound. So we got calcium, got fluorine. How many calciums do I have in calcium fluoride?
1.
1. How many fluorines do I have?
You have
2.
2.
2. Okay. What is the molar mass of calcium?
It's 40.
40. Okay. 40 grams per mole. What's the molar mass of fluorine?
18.
19.
Okay. 19 grams per mole. So calcium is going to contribute 40 grams per mole for this. Fluorine is going to contribute 38 grams per mole. So altogether, what is the molar mass of calcium fluoride?
It's
78 grams.
78 grams per mole.
Yeah. 78 grams per mole. So now we can find the molar mass of any compound given, right? Because we know how to find the molar mass of individual elements. And all you do to find the molar mass of compounds is you're going to find the individual molar mass of each element and add them together. So that makes sense?
Yeah.
Cole, I have a question about the calcium.
Yes.
Oh, wait, never mind. So the 40 gram per mole is the atomic mass from the periodic table?
It's the mass associated with calcium on the periodic table.
Okay, thank you.
Okay. So let's look. So now we can combine this all together. So if I give you, let's say, 0.0360 moles of barium chloride. So that's going to be your given, and I want grams. Let's do given. How would I go about to get this? How would I go from moles to grams?
Would you times it by 6.022 times 10 to the 23rd?
No, not quite, because we use Avogadro's number if we want to go from moles to molecules.
I said we need to find, first of all, like the formula for barium chloride.
Okay, yeah, that's a good place to start. We need to find the formula for barium chloride.
So it would be Ba chlorine 2.
BlCl2, barium chloride. Okay, now what's my next step from here?
We need to find the atomic mass of each atom.
So you said atomic mass?
Yeah.
Does atomic mass have to deal with grams?
Would it be molar mass?
There we go. We want to find the molar mass because we have moles and we want to get to grams. And molar mass does just that. It gives us grams and moles. So we need to find the molar mass of barium chloride. So what is the molar mass of barium chloride?
So we have 1 of barium, 2 of chloride.
Okay,
207 grams per mole.
207 grams. How'd you get that?
It's 137 for
I got the 137 for the barium, and then the 2 chlorines, I got 70. So then I added them.
So yeah, that would give you 207 grams per mole.
So I'm gonna chime in here again.
Oh,
I
you
love
made it
chiming
home.
in. No, I'm just you're doing a great job. So the thing is that for chlorine, isn't that 35.45 grams per mole?
Sure is.
And if I remember right, barium is 137.3.
Yes.
Okay, so this is one of those cases where we want to be careful about rounding, right? Because this guy is pretty darn close. If we have 2 of these, this is pretty darn close to 1. So that's the difference between 208 and 207. You know, because you multiply this guy by 2. And so if you think about it, 207, 208, I mean, that's what is a 0.5% off, but it still can make a difference when you're trying to do, be pretty precise. So you want to be kind of careful about when you round. Like when we talked about oxygen is like 15.9995 or something like that, right? It's okay to round in that case because you're so far off from that. Does that make sense?
Yes, it does.
Mm-hmm.
So, sorry, now go ahead, Cole, my bad.
Okay. So let's account for rounding. So 137.3 grams per mole. Then we have 2 chlorines that are each going to be that 35.45. Okay, so we can add these up. And do we all remember how to take into account for sig figs when we're adding? Daisy, do you remember how to do sig figs when we add?
Isn't it when it's 5, we round up, and then 4 and below, we keep it the same, right?
So when it's exactly 5, we're still going to round down, but if it's like 5-1, then we would round up. But so you're telling me I can just add like this. So 8, 12, 10, 18, like that, and I'm good to go.
No, you're not.
Okay, what else do I have to do?
The answer is 208.2.
Mm-hmm. So you tell me that this 0, what happens to this 0?
It goes away because you round to the number with the least significant figures after the decimal.
Right, so we want to look at the decimal and we want to see which one of them is least precise. So chlorine goes to the hundredths, while this barium only goes to the tenths. So when we're rounding, we want to make sure that when we round for sig figs for adding and subtracting, gonna round to the least precise, which is going to be that 208.2 grams per mole. Okay, so now we have the molar mass of this barium chloride, right?
Yes.
So now how am I going to use this to convert moles into grams?
Oh, we can use dimensional analysis.
Dimensional analysis, right?
Yeah, we're going to start with our given and use dimensional analysis. So we have 0.0360 moles barium chloride.
And then would it be 1 mole? And then on top 208.2.
So I want to put 1 mole of barium chloride and that 208.2 grams of barium chloride. Okay.
So your answer would be 7.50 grams over mole.
So is it going to be grams over moles?
Oh no, grams.
Grams. Why is it just grams?
Oh, that's because the mole cancel out.
Yeah, we crossed out the moles of barium chloride with dimensional analysis. And how come it's 7.50, not like 7.502?
That's because I rounded up and I just need 3 sig figs.
Yeah, you just need 3 sig figs because when we're multiplying, we just take the least amount, or we take the least amount of sig figs in the numbers. And the number that we started with
This case is
only has 3 sig figs, even though the number that we got from the barium chloride molar mass had 4 sig figs.
We also know that when we're using the periodic table, those numbers have been kind of rounded and stuff like that. So we never want to use those to determine our number of significant figures. We're always going to be using that given in that case.
Because we know for sure that that's like the amount of sig figs that we have.
That's correct. Okay, so at this point, you guys should be pretty comfortable with understanding that we have units. So when we make reference to those units, we could be talking about molecules, we could be talking about atoms, we could be talking about ions, we could be talking about girlfriend, right? And so if I was talking about those things, I'm going to use, if I want to determine the number of moles, I'm going to use Avogadro's number. And that's what that capital NA stands for, Avogadro's number, or Avogadro's constant. Okay, so that's going to be able to convert those molecules or atoms into moles. Okay, now if I want to go from moles to mass, then I'm going to use molar mass, which is grams per mole. Okay, and so you need to be able to move in both of those directions, going both ways, right? Are you with me?
Yes.
Yeah.
Yes, Dr. Henry.
Yes.
Okay. Okay. So this slide here is just basically telling you exactly the same thing. So if you're giving something in grams, you're going to use molar mass to sit there and convert to moles. And then if you have moles, because we know moles is quantity, right? And quantity, if we want to go from quantity or the number of moles to quantity, the actual quantity of what we're looking at, then we're going to use Avogadro's number. Okay, so let's see if you guys can test those skills. Determine the mass in grams of 3.2 times 10 to the 24th molecules of sulfur tetrafluoride. So where am I going to start?
By writing the chemical formula of sulfur tetrafluoride.
Okay, so what is the chemical formula?
That would be
Is it
S2F4.
ST5?
You said S,
2.
F4.
F4. Okay, SF4. Okay, sulfur, and then we have 4 fluorine. Okay, so that gives us the chemical formula. So what am I going to do next?
You need to
What am I
balance it
given?
out.
What was that?
So you need to balance it out if you have fluorine, so you need 2 sulfur. So that gives 4 and 4.
I don't know. You tell me.
It's
That's what I'm
covalent, so you don't
saying,
have to
S2.
balance anything.
No. So this
You're
is
right.
covalent, right? Remember, this is a covalent molecule. Sulfur and fluorine are both covalent. How do you write the chemical formula for those?
So you write the S and the F, and then
And this tells me how many F's I have. So this means I only have 1 sulfur, right? The only time you have to
Yeah.
balance it out is if it's an ionic compound. Is this an ionic compound?
No.
That's right. So we know that this is a covalent compound, right? Because ionic compounds are going to have metals and nonmetals, right? Right, Daisy?
Yes.
Okay, so don't forget that. That's important because otherwise you're going to put yourself on the wrong plane, right? And you want to remember covalent, you just do it based upon the numbers, right?
Okay. Thank you.
Don't forget the stuff that you've learned. It's important, okay? Make sure you go over it again before the exam.
I will do that. Thank you.
Okay. Okay, so now what do we do? So we have this guy. We know that that's the right chemical formula. Confident. Okay. So then what are we going to do next?
so you
Find the
Figure out how many you have of each.
sulfur 1 and then fluoride 4.
So we're going to do this because we want to find the what? What is it called?
Mass.
Okay, what type of mass?
Molar mass.
Molar mass. So we're looking to find the molar mass. Okay, so I have 1 sulfur and how many fluorines?
4.
4.
4.
4 fluorines. So sulfur weighs
32.06.
32.06. So that 0.6, I could probably get away with rounding that up to 32 even. And that's grams per mole. And we have one of those, right? So that's times 1. Okay, what about the fluorine?
18.998.
So can I get away with
19.
rounding that up to 19?
19.
Yeah.
Okay. Moles, not mils. Okay, and there's how many of those?
4.
4.
Okay. So 32 times 1 is 32. 19 times 4 is
76.
okay. We add these guys together.
108.
Grams per mole.
Okay. So I have the molar mass now. What am I going to do now?
You need to we need to do dimensional analysis by starting with your given.
Okay, I want to start with my given. This is my given. I'm going to start with that. Okay, so I have 3.2 times 10 to the 24th molecules of SF. Okay, so then what am I going to do?
And then we'll have 1 mole on the bottom.
Ah,
And then
so you're telling me molecules and moles are the same thing? They're the same type of units?
would it be
One
mole here?
molecule goes on the bottom.
Okay, so I'm going to do what you guys tell me because I'm here to look cute. And then I'm going to kind of question you on that. So 1 molecule.
Didn't we use Avogadro's number?
Ah, that sounds a little bit better because we know that Avogadro's number could be molecules, right?
Yes.
And we know that that's equal to 1 mole. Does that make sense?
Yes, it does.
Yeah.
Yeah.
Okay, so what is Avogadro's number? I'm old, I can't remember those things, so you got to help me.
6.022 times 10 to the 23rd molecules.
Okay, 6.022 times 10 to the 23rd. And that's molecules. Per 1 mole of SF4. Okay, so let's just kind of keep track of things. I get carried away sometimes. So those molecules are going to cancel out and we're left with moles. Okay, so I want grams. So how am I going to get to grams?
108 grams over 1 mole.
Oh, okay, so I have 108 grams over 1 mole. Okay, so then moles are going to cancel out and we're left with grams. That's what we want, right?
Yes.
Okay. So what else do I need to pay attention to?
Significant figures.
Sig figs. So how many sig figs am I going to have?
2.
2. Excellent. Okay, so somebody do the math for me.
It's going to be 5.7 times 10 to the 2. 10 to the second power.
7 times. And that is in grams. So 570 grams. Okay, questions, concerns? Cash? Okay, so this here is like a problem that you may end up seeing on the test, not this test that's coming up, but it brings everything together. It's that nomenclature, And now it's using that quantity and dimensional analysis, the stuff that we learned in the very, very beginning. Okay, so we're pulling it all together, right? So are you starting to feel like chemists yet?
Bad ones, but yeah.
Bad ones. No, you're gonna be good ones after I'm done. Come on, we're not done yet. We're getting you there. Okay. Okay, so let's get to the next question. Any questions on this?
No.
Good. So let's make it a little bit more complicated. So I'm going to talk to you guys about percent composition by mass. Percent composition by mass is, it's basically, you're looking at the part. So if we have part A and part B, so we have two things that we're bringing together, right? So percent composition is looking at the mass of part A divided by the total of part A and part B, okay? So we're assuming in this case we have a compound that is made of A, B, right? Okay, so, and we multiply that times 100 and we get percent mass. So for example, here we can calculate the percent mass of fluorine in calcium fluoride. So we know how much, we know the molar mass of chlorine, and we know the molar mass of fluoride. So we need to figure out how much fluorine that we have in calcium fluoride. So how would we go about doing that? What do you guys think? If we're looking at the part over the whole. So what would be the first thing that I would want to do?
Need to find the chemical formula.
We need to find the chemical formula, okay? So what is the chemical formula?
Would it be CAF2?
CAF2. Okay, so we got the chemical formula. So if we're looking at the part, and this part that we're looking for fluorine. So we want to know how much fluorine is in calcium fluoride. So what do you think I'm going to do next?
First of all, like how many of each atoms do we have?
Okay.
Identify.
So how many calciums do we have?
One.
One. Okay. Calcium weighs?
Would it be 40.078?
40.078. So can we just say 40?
Yes.
Okay. Okay. And fluorine?
It's 19.
19,
Okay. And how many of those do we have?
2, so 38.
So 2 times 19. Okay, we add them together. What do we get?
78. Grams per mole.
Okay. Okay, so then that gives me the whole, right? Or the total. Okay. So that gives me the mass of the total. So if I'm looking for the mass of the part divided by the mass of the total, what do you think I'm going to do?
38 divided by 78.
38 divided by 78. Exactly. And then we're going to multiply that by 100. And that's going to give me my percent mass of fluorine and calcium fluoride. Oops. Let me fix that up so it doesn't look too bad. Okay, so what do you guys get?
48.7.
You said 48.7? Okay, so if I wanted to figure out how much calcium we have in calcium fluoride, what could I do?
Would it be 40 over you need to divide 40 by 78 and then multiply by 100?
So I would just do.
Or you
yeah.
can subtract 100 by the 48.7.
That is correct. Or I could subtract it by 100. So I could do it this way. and I should end up with the same number, which is, what is that? 40, no, it would be 51.3.
51.3.
Yeah. Or we could just go 100 minus 48.7.
That's 51.3.
Okay. Questions, concerns, Cash?
Nope.
Okay. Let's see those skills work now. So it says calculate the percent composition of mass of aluminum sulfate. First thing I'm going to do,
Find the chemical formula.
find the chemical formula. What's the chemical formula?
Al2SO4.
Okay, Al2SO4. So now I want to calculate. It says, so here's the thing here, right? This is kind of a nice little question because they want you to do a lot more work. So calculate the percent composition by mass of aluminum sulfate. So they want you to do for each of the individual atoms in aluminum sulfate. So what am I going to do next?
Identify how many.
Okay.
Of each element you have, of each atom you have.
So I have how many aluminum?
2.
Okay. How much does aluminum weigh?
It weighs 26.982. 27.
27. Okay.
Mm-hmm.
– 27 times 2 is 54.
Yes.
Okay. Sulfur, how many sulfurs do we have?
1.
Oh, wait, is this balanced? Did I forget something?
It's not balanced.
It's not balanced. So what did I forget?
To balance it out.
To balance, well, I forgot to balance it out. So what do I need to balance it out?
2.
I need a 2. So what is the charge on sulfate?
-2.
Sulfate is -2, right?
Only 3?
So I'll need 3 of those to balance it out because I know that aluminum is +3, right?
So it has 6.
Okay. So yeah, so then now it's 6. Good job. Okay. So how many sulfurs do I have now?
3.
3. Okay. So sulfur weighs
32.
32 grams per mole. 3 times 32 is 96. You better check my math. Oxygen. How many oxygens do I have?
12.
12. Oxygen weighs
16.
16.
Yes.
12 times 16.
192.
Okay, so we add these all together.
342 grams per mole.
Okay, so now we have the molar mass of aluminum sulfate. what am I going to do next? How am I going to calculate the percent composition of each?
You take the each
You take the mass of each and divide it by the total.
Okay,
right? And then you
that's
multiply
correct.
it by 100.
Okay. So we'll start with aluminum. Mass of the total mass of aluminum,
54 grams per mole.
54 grams per mole. We're going to divide it by
342
342
times 100.
times 100. And that's going to give me
100.15.
You said it gives you 100.15?
Well, maybe I did something wrong. Hold on.
15.8.
What did you get? I heard 100.15 and then I heard something 0.8.
Gonna be
15.8.
15.8.
Can you write it on the board? Because I can hardly hear you. Ah, 15.78. Okay, and that's percent. And that's of aluminum. Okay, what about sulfur? What am I going to do for sulfur?
28.1.
28. Oh, you already calculated it for me. Tell me, Mike, the steps. Don't just give me the answers.
Okay. We're doing sulfur, right? So it would be
Yeah.
96 divided by 342 times 100.
Okay. And that's giving me, you said 28 point.
1%.
Okay. And then our oxygen, we have two ways of doing it. We can do it the way that we're doing everything else.
Or adding them up with the sulfur and aluminum and then subtracting by 100.
Okay. So we show this way first and then we'll do the other way.
Dr. Henry, I had a question.
Yep.
So when we multiply it by 100, we multiply it by the actual 100 and not the decimal?
Yeah, you're multiplying it by 100% because we want percent, not the fraction.
Oh,
So if
yeah.
I want it mass fraction, then we
Yeah.
wouldn't have to multiply it by anything.
Oh,
right.
okay. Thank you.
Okay. So Daisy, I know you've calculated it. What's the answer?
Oh, it's 56.12.
56.
Oh no,
15.
56.14.
Okay. You said 56.14 or 56.12?
It's 56.14.
That's when I do it, but when I do it like adding then subtracting, I get
Uh-huh.
56.12.
Okay.
Yeah.
So that's better because it adds up to 100.
Oh, okay. So this one is a little bit over. And then if we do it the other way, we get 100 minus 15.78 minus 28, and that equals 56.12. Okay. Questions, concerns, Cash?
No.
Is
Piece
this
of
gonna
cake?
be on the exam?
No, this is not going to be on the upcoming exam. This will be on your next exam. But if you want it, I can make the change. You know, I have time. It's okay?
We're good.
For extra credit, maybe?
About extra credit, yeah.
Yeah.
About some extra credit. Okay. We'll see about that. It's negotiable. Okay, let me clear this. How are we doing on time?
6:24.
Okay, we're doing good actually. Okay, let's see. Okay. So here's a question for you. Aluminum chlorate is 38.35% chloride. What mass of aluminum chlorate is needed as a source of 50.0 milligrams of chloride? Okay, so in this case, what are they giving us?
The
The
percentage.
percentage.
They're giving us the percentage already, so we don't have to calculate the percentage. Okay, so we know that we have 38.35% chloride. Okay, that's going to equal, what is that equation? How do I calculate the mass percent?
You do it by the. It's like the mass of the number, and then
The Avogadro number?
you then divide by
Ooh,
the
just
overall mass,
molar
and
mass.
then times 100.
Okay, so in the past we used the molar mass, but what are we looking at? We're looking at the mass of, are we looking at the mass of the part, the whole, or nothing? What are we looking at? So what
Mass
was the equation that we just used to calculate all of the other ones? It was,
It's
Molar mass.
parts
yeah,
of
Part
it.
A.
so
over
you're
the
using
total.
it, okay, so you guys are getting caught up on the exactness of it. Don't think about the exactness, tell me generally, what are we looking at? So how do we do the calculation? Generally,
Like A
so we
divided
can
by B.
apply it to everything else, right?
Chemical formula.
Parts of A divided by the total part.
Okay, so it's parts divided by the total part. So it's the mass of parts divided by the total part. So whether I'm working with molar mass or whether I'm working with actual mass, I should be able to figure out it's part over the whole. Okay, you guys get that?
Yes.
Yes.
So don't get caught up. And I've noticed this. You guys kind of get caught up in exactly. This is what I do exactly. So when you get something that isn't what you do exactly, you're like, what in the hell do I do? Right? So you kind of have to look at the, learn from that example to apply it to bigger things. Because we're talking about mass in general, whether it's molar mass or whether it's just mass that we're working with. So here they're telling us that the percent mass is 38.35% of chlorine, right? And then they go on and says, what mass of aluminum chlorate is needed as a source of 50.0 milligrams of chloride? So what do I know? What else are they giving me here?
You're given
50.0 milligrams of chloride.
Okay, so is that the part or is that a whole?
Oh,
50.4 milligrams. Write it out for me. 50.0 milligrams, mg, of chloride. Is that the part
it's a
or is that
part.
the whole?
Part.
It's the part, because we know that aluminum chlorate looks like what?
Would it be Al ClO3? And then you need parentheses. Would it be 3 and 2? So you need 2 aluminum.
Do I need 2 aluminums? What is the charge on chlorate?
-1. You just need 3 of the chlorates.
I'll need 3 of the chlorates. So you need to pay attention to the charge of the other guy, right? You need to know this, because if you don't know this, it's going to burn you every time and you're going to get annihilated on this next test, right? It's a necessity. Now you guys are starting to see why you need to know your nomenclature. It's important. Make sure you understand it. If you're not understanding it, make sure you come and see me, come and see Cole, come and see Israel, Haley, oops,
and that's 3. Okay, so you want to make sure that you guys got that down, right? Okay, so we know that chlorine is only part. So we know we're going to have 50 grams or 50 milligrams of this guy, of the chlorine. And so we're trying to find, we're going to use X milligrams because milligrams cancel out, and that gives me my percentage, times 100 of our aluminum chlorate. Okay. So how can I solve for X?
Divide by 100 on both sides.
Divide by 100 on both sides.
Would you just multiply oh, never mind. Multiply across maybe?
Cross multiply, huh? So if I cross multiply and get X by itself, would that allow me to solve for X? So in other words, I say X over here and X over here. So then the X is going to cancel out. On this side, we get 38.35% Cl X, and then of course that's going to be X Mg Al C ClO3. Okay. Erase this. And then that's going to equal
50.0.
So 50.0 milligrams times 100. That should be times, I shouldn't use X. 100. Okay, so 100 times 50 is what?
5,000.
Okay. 5,000. Okay, the units are going to end up canceling out because this percentage is, when we divide that by here, we'll get X milligrams.
Wouldn't the 100 go away once you multiplied them?
Yeah. Well, oh yeah, thank you. Down here. Yes. And your percentages are going to cancel out. And then you're just going to be left with milligrams. Okay, so
How did the 38 move to the other side?
I divided both sides by 38 because this is 38 over here, right? So, because that's what I started with on this side of the equation. So if I divide this by 38.35%, and I divide this guy by 38, because what I do to one side, I have to do to the other side. %. So then I get 5,000 over 38.35. I keep forgetting, I get excited and I want to skip steps. So these guys are going to cancel each other out. What did you guys get?
130.
130.3.
130.3. And if we, how many sig figs should I have?
4.
How many sig figs should I have?
3.
Oh.
3.
3. So the answer should be 130. That's milligrams of aluminum chlorate. Okay, questions, concerns, Cash? Okay, so real quick, so don't get bogged down by the specific. You want to make sure that you understand the concept because you need to be able to apply it to more than just the specific. Okay. Okay. Let's see. Okay, empirical formulas. How are you guys feeling right now? Feeling good?
So,
Yeah, that last
Okay.
one was a little.
What was that?
That last one was a little trickier than the other ones, but
Yeah.
yeah.
Yeah, I mean, because and it's because you guys are still, it's that process of learning, you know, and when we're kind of young at learning, we learn stuff, but we're like, we want to learn it exactly how to do it this way. And then you don't think about it in a bigger picture. And so, but when you start getting used to learning, you know, you start learning, oh yeah, I could apply this to this. Oh yeah, I could apply this to this. Oh yeah, I could apply this to this. And so that's where I want to get you guys at, right? I want you guys to be able to apply to other things. So, because then that means you're ripe for learning, really learning. Then you can start doing crazy stuff. Okay. So the next thing we want to talk about is called empirical formulas. Empirical formulas is basically it's representing the lowest integral ratio between all of the elements in a compound. So let me give you an example. So if I have C6, H12, O6. So the empirical formula would give me the lowest, we would find the lowest common denominator in all of those and divide it by that. Okay, so what is the thing that we could divide all of these guys by?
6.
6. Okay, so if we divide everything by 6, we get C, H what? 2, and O. Okay, so this would be the empirical formula of this. Does that make sense?
Yeah.
Yes. Why did you say that we do this again?
And the 2 is because of
Because 12, 6 divided by 12. And you know that if there's nothing there, that means that it's 1, right?
oh, okay, got it.
Okay.
So the concept is to divide it by the lowest number within the formula or within.
Yeah, so you want to get it so it gives you the lowest possible integral ratio that you can have. So if you look at this, right? So if I divide this by 6, that's going to give me 1, because you can't go any lower than 1, any whole number lower than 1, right? 1 is it. So it's greatest common denominator, yes, or greatest common factor. So you're going to divide this all by 6 to give me the lowest possible integral ratio. So 1 to 1. Does that make sense?
Can you do another one of those?
Sure.
Why did you
So-
say, why do we do these? Like, what's the reason that we have to find their lowest? Like, why do we simplify them so much?
We simplify them so much because you're going to use empirical formulas to sit there and determine real molecules. So you're going to be able to go the other way. So sometimes when we're doing chemical analysis, we'll do an experiment and it won't give us the actual molecule, but it'll give us the empirical formula. From that empirical formula, you need to be able to figure out how to get the real molecule. And I'm going to show you how to do that.
Okay.
Okay. So, but the first thing is you need to understand how to get the empirical formula from data that you're collecting. Okay. So here we have C4, H5. So what would be the empirical formula of that?
Divided by 2, so we C2H5.
Okay. Piece of cake?
Yes.
Okay, good. Okay, so the way that we determine empirical formulas, sometimes you're going to be given percent mass, right? And so when you're given percent mass is based upon mass. So we know that that compound, the total mass of that compound under ideal circumstances is going to be 100%, right? And so we can assume that if we have that compound, altogether it should weigh 100 grams. And then if we got, let's say, 5% of one part of it, 10% of the other part, so then we know that one part of it is 5%, then we can say that that's 5 grams. One part is 10 grams, and then the rest of it would be whatever that last component is. Okay. Let me show you what I mean, because that'll help. The other thing is we're going to use that mole ratio. So we need to be able to convert into moles, because when we look at those numbers, this tells me that I have 1 carbon, 2 hydrogens, 1 oxygen, right? It doesn't say I have 5 grams of carbon, right? Or 1 gram of carbon. It says that I have 1 carbon in that molecule, not the mass. So we need to make sure that we convert the mass into moles, okay? And so we want to be looking at moles, because moles is quantity. Are you with me? Do you guys understand what I mean by that?
Can you repeat it one more time?
I said we want to make sure that we convert grams or mass into moles so that we can compare the moles, because the moles are quantity, just like these. This is 1 carbon. This is 2 hydrogens. This is 1 oxygen, right? It's not the mass of those guys. It's the moles of them, okay? Does that make sense?
So you're saying that after being simplified into C, H2, and then O, it's still going to have the same mass as C6, H12, or?
No, I'm not saying that.
Oh, okay.
What I'm saying is it'll have the same mass ratio as that, but it won't have the same mass, okay? So what I'm saying is that this here is 1 carbon. This here is 2 hydrogens. This here is 1 oxygen, okay? Because we have that ratio, it's based upon quantity. It's not based upon mass, right? So we're not saying that this is 1 mass of carbon. This is 2 mass of hydrogen. This is 1 mass of oxygen. We're not saying that. We're saying it's quantity. We know that we have 1 of those, right? It's kind of like, okay, so there are 3 people that I see on my screen. I see Clarissa, I see Sienna, and I see Kayla, right? They're each 3 individuals. Now, I don't know their weights. They're each 3 individuals. I know I have 3. I have 1 Clarissa, I have 1 Sienna, and I have 1 Kayla, okay? So in other words, I need to make sure I get quantity, right? So I need to make sure that if I'm given mass, I can change that into quantity, how many of them I have. Does that make sense?
I feel like it'll make more sense if you show us how to do it.
Okay.
Okay.
And then I'll give you another analogy, even better one. Okay, so for instance, a sample of pure compound is made up of 1.61 grams of phosphorus and 2.98 grams of fluorine. Find the empirical formula of the compound. Okay, so in this case, the first thing I want to do, since this is in grams, it's in mass, what do I want to do first?
Calculate
If I want quantity, what is the thing that I want to do?
molar mass?
I'm going to use my molar mass. Yeah, that's true. So I'm going to use my molar mass to change it to moles, right? Because moles represent quantity. So that's 1.61 grams of phosphorus. What is the chemical symbol for phosphorus?
P.
P.
Okay, and how much does P weigh?
30?
30.
Is it 31?
31. So is 31, what are the units?
Grams per mole.
Grams per 1 mole, right? Of phosphorus.
Where did 31 come from again?
Where did you
It's
guys
how
get
much-
31 from?
From
It's
the
how
periodic
much,
table, it's the atomic mass of phosphorus.
So
and
we
then
use our
round it up.
In your periodic table.
periodic table.
But you just rounded it up instead of, because it says 30.97.4, then you round it up to 31.
Just to make our calculations easier. Okay, so grams are going to cancel out and we're left with just moles. What do you guys get? Who's my calculator?
Would it be 0.052?
0.0. You said 552 or
519.
519? Okay, and we have how many sig figs?
3.
3. Okay, and that's moles of phosphorus.
Phosphorus.
Okay, and then fluorine. We're starting with our given. So what am I going to do here?
Then the units are 1 mole over 19 grams. And 19 is because that's the mass of fluorine.
Okay.
That would be 0.157.
Okay, so this allows me to compare the two to each other, right? So since I have them in moles, I can kind of figure out the quantity. The way that I would do that is by dividing by the smallest. Which one is smallest, phosphorus or fluorine?
Phosphorus.
Okay. So if I divide both of them by phosphorus, let's see. So we divide phosphorus by itself. So that's going to equal what?
1.
1.
And then if I divide this one by that same number,
.03.
okay. So this is 3.03. Now, the numbers, when we have those numbers, they're whole numbers, right? So if this number is close to, let's say, really, really close to a whole number, you can round up. So in this case, we'd round this up to 3. Okay, so then that means that my chemical formula is going to be PF3. Okay.
And that's because there's 1 phosphorus and then 3 of the fluorine, right?
Can you repeat that, please?
That's because there's 1 phosphorus and 3 fluorine.
That's right. Yeah. And so that gives me the ratio between them. So we have to get the number of moles to determine that ratio. Okay. And we know that that ratio is going to be a whole number ratio, right? Because you're not going to have a half of a molecule or a third of a molecule or 0.03 of a molecule. Okay.
And why do we divide by 0.0519 for both instead of 0.157 for both?
because the 0.157 is a higher number, and you want to set it up so that you have the right ratio. If you divide it by the 0.57, then you're going to have a half of a, or a third of something, right? Because you're not going to end up with a whole number, and that doesn't make sense, does it?
No.
So you always want to divide it by the smallest number, because then that gives you the ratio. So you know that one of them is going to be 1, and the other ones are going to be because remember, we're looking for the empirical formula. 1 and 1 is going to be like either 2 or 3 or something like that. Okay. Are you with me?
Yes.
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 Okay. So give me 1 second. Let me calculate something real quick. Okay, so let's assume that we have, instead of this number, I'm going to cross this out. Did everybody get this down?
Yes.
And,
Yeah.
and by the way, you guys are asking all the right questions. You know, keep asking those questions. They're really good questions. I love that why. Okay, so let's assume that we have that number. Okay, so this guy is going to be exactly the same, so we're not going to have to redo that. This is going to change. Okay. So if I do that, this number here is going to be what?
0.173.
Okay. And then if I divide that by,
That would be 3.23.
3.23.
Mhm.
Are you sure that's 3.23 and not 3.33?
It's 3.33, Dr. Henry.
Okay, 3.33. Okay. Daisy talks so soft that I could hardly hear her. Okay, so it's 3.33. So now this is a different circumstance, because if you think about it, 3.33 is like a third of something, right? Is that correct? 1/3 is the same thing as 0.33. It's about a third, right? Okay, so this tells us something else is going on, right? So if it's not really, really close to a whole number, and you have a number like 0.33, that means that we need to figure out what we need to multiply it by so it will be a whole number. So what would I multiply 1/3 by so I can make it a whole number?
3.
I'd multiply it by 3. So I would multiply this by 3 and I'd multiply that by 3. Okay, and then that would change our chemical formula. So I'm going to do that, purple. So 3.33333 times 3, if I remember correctly, it's going to be 10.
10.
And this is going to be 3. So in this case, this chemical formula, just by that change there in the amount that we have, lets us know that this chemical formula would be P3F10. Okay.
I like these.
You said you like these?
Yeah.
Okay. Okay. So I'm going to give you this nice little cheat sheet that I wish I had when I was in college. So if it ends with 0.2, we need to multiply it by what to make it a whole number?
5.
If it ends in 0.33, we need to multiply it by what?
3.
3.
If it ends in 0.25, we need to multiply it by what?
4.
4.
If it ends in 0.5, we need to multiply it by
2.
2.
0.66.
One.
Times 3.
6.
3, because 3 would give me a whole number. 6 wouldn't, and 1 definitely wouldn't, right? So if we multiply 0.33, that's going to be 2/3, so then that'll be equal to 2, right? And if I have 0.75,
Times 4.
and 0.8.
Is it going to be 5 again?
It's going to be 5 again. Okay, see the little trend? Okay,
And then
so
for the one that's a 0.66, when you multiply it by 3 is 1.98.
yeah, which is really close because really it's 0.66666666. So maybe I should do this to make it.
So wouldn't we
Is
run
that
it
better?
to-
So if you get 1.98, that's pretty much 2, right? Because that's really close.
Okay, got it.
So and so your goal is to try to get in that 0.9 area, because then that's a good area. So if you're within that 0.9 area, it's okay to round. Okay. Or slightly over it. So if you're like 3.05, it's okay to round down in that case. Okay. That's the last thing, and then we'll go to lab. Okay, so we've talked about percent mass. So here's a case. We have nicotine is 74.1% carbon, 8.64% hydrogen, and 17.3% nitrogen. So what is the empirical formula for this? Okay. So in this case, we have percent mass. So here, this is the point where you can make the assumption. If we have assumed that we have 100 grams of nicotine, how much of it will be carbon?
74.1.
So 74.1 grams would be carbon, right? How much would be hydrogen?
8.64.
8.64. And then how much would be nitrogen?
17.3. 10.3.
Okay. So okay, so then the first thing I want to do is do what?
Sorry, that's a G, right? 100 G.
Yeah, that's 100 G. Yeah.
Oh.
Find
So
the,
then the first thing I want to do is do what?
find the mole of each element.
Find the mole of each element. Okay, how do I do that?
1 mole over their atomic mass. So for carbon, it's going to be 12. 1 mole over 12.
1 mole over 12 grams. See? What do you guys get?
6.175.
6.175.
Yes.
Okay. How many sig figs should I have here?
3.
3.
6.18.
Okay. And that's moles. Okay, the next one.
It's just going to be 8.64 moles per of hydrogen again.
That 1 mole of hydrogen weighs 1 gram.
Yes.
Oops. And then nitrogen.
1 mole over 14.
Okay.
It equals 1.24 moles of nitrogen.
You said 1.24. Oops. Okay, my next step.
Divide by the lowest number, or the lowest one, right?
Okay. And which one is that?
The 1.24.
Okay, so what do we get for carbon? And remember what?
98.
Set 2.98. So is that close enough to 3 to round it up?
That's 4.98.
Oh, you said 4.98. My bad. Is that close enough to 5 to round it up?
Yes.
Yeah.
Okay. The hydrogen?
6.96.
7.
97.
So you said 6.97.
Yes.
Okay, what do you guys get?
7.
7.
7.
And then nitrogen?
1.
1.
Okay, so my chemical formula would be C5H7N. Okay, piece of cake?
Yes.
I have a question.
Yes.
I missed the part where you got the 1.24. How did you get 1.24 in that green one? Oh, the denominator.
On the denominator, because we divide it by everything by the smallest number. So we got 1.24 here. That's smaller than all of the rest. So you use that to divide everything by. So you're using that as your comparison to everything else.
Oh, okay. Thank you.
No problem.
Does it matter how we write the chemical formula?
It typically does. So carbon has a tendency of going first, and then hydrogen, and then the one that is the most electronegative goes last.
Okay.
Okay. And then if you're talking about an ionic compound, you know that the metal goes first, and then the non-metal goes last.
Yes.
Okay. So we're going to stop here, and I'll meet you guys in